Physics depends on measurement. Every number we trust, every constant we quote, every prediction we verify begins with an act of measuring something: length, time, mass, charge, and energy. The entire structure of science rests on the assumption that measurement reveals what is there. And most of the time, this assumption works so well that it barely feels like an assumption at all. But when measurement is examined at the foundations of physics, it becomes strangely difficult to say what it actually is. Not how accurate it is, not how precise our instruments are. Instead, the question is what a measurement physically consists of, and why it produces a single, definite result. Modern physics can calculate measurement outcomes with extraordinary reliability. It can predict distributions, averages, and probabilities with astonishing accuracy. Entire technologies depend on this predictive success. And yet, the theories themselves do not describe measurement as a physical process in the same way they describe motion, interaction, or change. Instead, measurement appears as something that happens to a system rather than something the system itself explains. In everyday life, measurement feels straightforward. You place a ruler next to an object. You start a stopwatch. You weigh something on a scale. There is an object, and measurement simply reveals a property the object already has. The act of measuring is treated as passive, almost invisible. But the deeper physics looks, the less this picture holds. The equations that govern physical systems describe continuous evolution. They tell us how a system changes over time, how variables interact, how states transform. These equations work whether anyone is observing the system or not. They make no reference to instruments, observers, or results. They simply describe how physical quantities evolve. Measurement enters only later as an additional step, a rule applied after the fact. Theory tells us how a system evolves. Measurement tells us what we see, but the theory does not explain how one becomes the other. This creates a quiet but persistent gap. Before a measurement, the system is described in one way. After a measurement, it is described in another. The transition between these two descriptions is not derived from the same principles that govern the rest of the theory. It is introduced separately because it has to be. This is not a failure of calculation. The predictions work. The numbers come out right. The gap exists not in the results, but in the meaning we assign to them. Physics can tell us the probability that a detector will register a certain value. It can tell us how often that value will appear if the experiment is repeated many times. It can tell us how results will cluster and converge. What it cannot tell us in a single unified way is why one particular outcome occurs instead of another when the measurement is made. Different frameworks describe this transition differently. Some treat it as a physical interaction. Others treat it as an update of information. Others avoid describing it at all. But despite these differences, the core predictive machinery remains unchanged, which means that the success of physics does not depend on resolving measurement at a fundamental level. That is the strange asymmetry. Measurement is essential, but it is not foundational. It is operational rather than ontological. It works without being fully defined. This becomes even clearer when we consider the role of instruments. It is tempting to think that measurement problems arise because our tools are imperfect, that with better detectors, greater isolation, or finer resolution, the issue would disappear. But this is not the case. The gap remains even in idealized experiments, even when noise is eliminated, even when systems are perfectly controlled. The problem is not what is being measured or how carefully it is measured. The problem is how measurement becomes an event at all. At what point does an interaction stop being part of a system's evolution and start being a result? At what point does a physical process become a definite outcome? The theory does not specify this boundary, it assumes it. In practice, physicists handle this by adding measurement rules from outside the core equations. These rules are extremely effective. They allow predictions to be tested and confirmed to extraordinary precision, but they are not derived in the same way as the rest of the theory. They sit alongside it, not inside it. This is unusual. In most areas of physics, measurement emerges naturally from the dynamics of the system being studied. The same principles that describe motion also describe how motion is detected. At the foundations, this unity breaks. And yet physics continues anyway. This is not because physicists are unaware of the issue. The measurement problem has been recognized for decades. It is discussed openly, it is taught carefully, it is debated extensively, but none of this prevents the theory from working. Physics predicts outcomes without fully explaining what an outcome is. This pattern should feel familiar by now. In earlier cases, physics predicted particle behavior without being able to say what a particle actually is. It predicted laws without fully grounding what makes them laws. It predicted nothing without being able to define what nothing means. Measurement follows the same pattern. The system functions with extraordinary precision while leaving its most basic concepts underdefined. This does not mean physics is broken, it means physics is constrained. It operates within a framework where certain transitions are treated as given rather than derived, and where certain boundaries are accepted, because crossing them would require concepts the theory does not yet possess. Measurement feels fundamental because it is unavoidable. But at the deepest level, it is not resolved, it is assumed, and that assumption is rarely visible because the results are so reliable. The predictions are so accurate, the technologies built on them work so well, but reliability is not the same as explanation. Physics can calculate what measurements will show with remarkable confidence. It can tell us how often outcomes occur and how they relate to one another. What it cannot yet do is close the loop between physical process and measured reality in a single, self-contained description. The act that seems most basic in science remains one of its least well-defined at the foundations, and physics proceeds anyway because it can.